Hey, it's your friend Joseph Murphy. I heard you were interested in taking Foundations of Computer Science next semester. Lucky for you, I took it this semester. And I really want to help you learn. So I think the best way for me to do that is if I was to do an exercise from each chapter on this whiteboard in front of you. And then after, I'll also show you more exercises from each chapter on paper, and then I'll explain how I did them and all that. I know everyone learns different, so that way I feel like you'll be able to get both seeing me do it live and seeing the process of it, and then when I show you the paper and how I did it on the paper, it will be like a class where I'm the professor and I'm doing notes live with you at the beginning throughout the whole class, and then it will also be like a class where the professor just shows all of the notes at the beginning, because I know people like different ways, so that way you'll get both. But yeah, no, I think this way it will help you learn better, because it will show you both types of learning, and also I'll be able to tell you like what I liked, what I didn't like, what I struggled with, what I actually really learned from the textbook. So I'll be using the Introduction to Theory of Computing 2nd edition textbook for this exercise. Alright, so we start off with chapter 0, and it's just an introduction chapter. However, this is important because you need to know the stuff in the introduction for every chapter. It's really the groundwork of the course, so that's why we're doing an exercise from it, because without it, you'll be lost. So we're doing exercise 3 in chapter 0. This is just the question written over. There's no notes or anything. So the basis of this exercise is A equals the set of X, Y, and Z. B is the set of X, Y. Question, or part A is A a subset of B? And B is B a subset of A? So we're grouping these questions together because they both go together. Is A a subset of B? The answer to that is no. Is B a subset of A? The answer to that is yes. B is a subset of A because both elements found in B are also found in A. A is not a subset of B because all elements found in A are not found in B. Question C. What is A union B? Union is the joining of two sets. So the set of A union B would be X, Y, and Z. Part D. What is A intersect B? The set of A intersect B is basically what elements both sets have. Union is what elements all sets have. Intersect is what both have. So this set would just contain of X and Y, because both of those are found in both. E. What is A times B? So in order to do set multiplication, you take the first element of the first set, or you take the first element of the smaller set and multiply it by each element of the top, or combine it with each element of the top, and you do the same with the second. So this would be a set containing parentheses X, X, comma, parentheses X, Y, comma, parentheses X, Z, comma, parentheses Y, X, parentheses Y, Y, and finally parentheses Y, Z. And that's the whole set of A times B. F, the last part of this question, asks what is the power set of set B? A power set is all the elements, all the sets and possible all the sets of set B. So in order to answer this, the power set contains null, then comma, it contains a set of just x, comma, then it contains a set of just y, comma, then finally it contains a set of x, y. And that is the whole set. A way to find this out easier, that I always remember, is because there's two elements, a power set is always to the second power, so it's 2 to the second, which equals 4. So you should have 4 different things in the power set, which we have. Okay, moving on to chapter 1. So here are some of the exercises I did for chapter 1 as well. So the first one I did was 1-1, and it was the following state diagrams of the two DFAs, M1 and M2, answering the following questions about each. So here's M1, here's M2. As you can see, they both start at Q1. M1 has a accept state of Q2. M2 has a accept state of Q1 and Q4. Alright, so what's the start state? Q1 for both. What is this set of accepting states? Q2, Q1, and Q4. What sequence does the state of the machines go through for input AABB? AABB, so it goes Q1 to Q2, Q2 to Q3, Q3 to Q1, Q1 to Q1. Then this one it goes Q1 to Q1 to Q1 to Q2 to Q4. Does the machine accept this? We saw this one just ended at Q4, so yes. This one, it ends at Q1, so it does not. Does the machine accept string? Does the machine accept the empty string? No, because the empty string you just stay at Q1 at this one. Here, yes, because you start there and you end there. Alright, so now this question is based off of it, and it was give the formal description of the machines above. So a DFA are 5 tuples, with sigma being the alphabet, Q being the finite set of states, Q0 being the start state, delta being the transition function, and F being the accepting states. So M1's is, the alphabet is A and B, because that's what it can accept. The states are Q1, Q2, and Q3. The start state is Q1. Transition function's delta, and the accept state's Q2. And then for M2, same alphabet. The set of states is different because this one has Q4 in it. Same start states, same transition functions. However, this set of accepting states also has Q1 and Q4 because there's 2. Alright, given NFA recognizing the language, so this is, it ends in either 01, 0001, or 01, 001 or 010. So this means just any strings ending in those. So this would be an NFA. So any string ending in 01, it would 01 ends here. Any string ending in 001, so you want to do it 001 ends here in the accepting state. 010, 010 ends here accepting. It's a simple 2-state NFA for it. Now to convert it to its equivalent DFA, we need more steps. We need 2 more steps. So starts here, so say 01, 0. So if it ends in 01, 01 with the accept state, so it passes. Ends in 001. 0 stays in Q2, 1 ends in Q3. And then 010, 01, and then goes to Q4 at 0, passes. So basically, the key here is to make sure that it always ends. So say it goes here with a 0, and then another 0. That doesn't mess anything up for these two, or this one even, so you stay there. But like here, if you go, say 010, and you have another 1 there, you have to go back here because if not, it won't pass. So overall, I think one of the most successful things I learned from this textbook was how to convert NFAs to DFAs. It's just really a process, and you just really have to double check and make sure that every possible option is accounted for. And I believe from this textbook, I got really good at that. Alright, so then for this last exercise, a finite state transducer. So it gives you T1 and T2. So basically this means it starts in Q1, and when it reads a 0, it outputs a 0. When it reads a 1, it outputs a 1, and so forth for both of these. So it's asking for the output and then the sequence of states. So when T1 reads 0, 1, 1, it goes 0, 1, 1. So it just outputs 0, 0, 0. It stays here and never makes it across. For 2, 1, 1, it reads the 2 first, so then it outputs a 1, and now it's in Q2, and reads a 1, 1, so it outputs 2 1s. And then we jump to T2. So for BBAA, it would go B to Q3 and output a 1, B to Q2 output a 1, B to Q1 output, no, I meant A back to Q3 output a 1, and then B again to Q2 output a 1. So that would again be the output. And then we'll just go over sequence of states. So for like this one, the sequence of states, because it's 0, 1, 1, it never leaves Q1 because it always stays in it. And then for BBB, BBB, the sequence of states is Q1 to Q3 to Q2 to Q1 to Q3 to Q2 to Q1. It's just a circle for those 6. Okay, so for chapter 1, we're going to do exercise 27. Just the question here, no notes. So, question 27 uses exercise 24, which we actually just did and I just showed you. So, exercise 27 says, make a state diagram for a FST with the following behavior. The alphabet consists of 0 and 1s. So, its output, as you know, FST's input output just went over it. So its output is identical to its input on even, where does it say, positions. However, it is inverted on odd positions. So, the way I solve this, and the easiest way I think to do it, is to think back to the beginning of the chapter when we learned about just normal DFAs and even and odd, and how to do how to write a DFA state diagram that determines even or odd. So, the DFA state diagram to determine even and odd is even, odd. So it starts at even because 0 is technically even, I believe. And then 1, 0, 1. So, on a binary string, all you can have is 1 and 0s. So you read in a string of 1, 1, 1. You want the DFA to understand if it's, and you can only accept, say, odd strings. Let's say that. So the DFA would look like this, because you would start here and read the first one, go to odd. Then you read the second one, go back to even. Then you read the third one, and it would be an odd length. So you would end at odd. Now, in order to use this for a FST with output behavior identical depending on position, you would, well, keep that actually. So this is what the FST would look like. So you still want an even state. You don't label them actually. So you want a state there and a state here. So we know, because we just did this, that this is the even and this is the odd state. So the key is to have 0 equal 1 and 1 equals 0 when going to odd. But when going to even, 0, 0, 0 slash 0 and 1 slash 1. We know that means it reads a 0 and outputs a 0 when going back to even. So say we're giving a string of 0, 0, 0, 0, 1, 1, 1, 1. The output for this string would be, we read a 0, 1. We read another 0, 0. We're here, we read another 0, so it's a 1 again. Then we're here, we read another 0, 0. We read a 1, 0. Read a 1, 1. 1, so it's a 0. Then finally, the last one, we read a 1, so 1. This has no end state, technically. So we took input of this, and the output is this. So this will work with 1, 1. This will work with 0, 1, 1, 1. Say that's our input. So we output a 1, because we read the 0 first, on the odd position. Then on the even position, we read a 1, so we output a 1. Then here we read a 1 on the odd position, so we output a 0. Then here on the even position, we output a 1. So that is how you would write a FST, where the output is identical to input on the even positions, however it's inverted on the odd positions. Alright, so for chapter 2 exercise I did 2.1, and basically you're giving sequences kind of like A plus A plus A, and you have to write parse trees and the deviations. So most of them are simple, so I'm going to explain the complex one. So basically A plus A plus A, so you start off at the first plus, and that's a exponent, or what, equation kind of, term, factor, yeah. So the E breaks into ET, or just a T. So this is how you make the parse tree. The A's are all factors, and they go to terms, which terms can break down into more terms or factors, and term and factors. So the deviations is you start with E, and that gives you E plus T, and then you get T plus T, and then you get F plus T, so factor plus term, and then you get A plus T, which is, so you get the A from the factor, the T from the first E, so then it's, that T becomes T plus F, or T plus, yeah, so then you get A plus T plus F. That turns to A plus F plus F, and then it turns to A plus F, which turns to A plus A plus A. And that's a simple explanation of parse trees and deviations. And then this actually wasn't in the textbook, but this was from my, this was from exam 1, the mid-year, and I just thought it was very true, and it really helps with PDAs, because I didn't think the exercises in the textbook were that great with PDAs. So this basically shows you how every CFG can be converted into PDA. And it works because PDAs have CFGs as their language, or they have CFLs as a language, and CFGs equal CFLs. So basically, a simple CFG is S goes into A, capital A, B, capital B, A goes into lowercase a, B goes into B, capital A. So basically, if you're given AASB to convert it, it turns to AAAA, B, B, B. And then you just can keep going and see the different deviations. So PDAs can do that as well when they're giving states to change into, and then from there they can keep changing states. So this is a PDA of AASB, and then by the time you reach the accepting state, it will turn into AAAABABA. So that's how CFGs can be converted into PDAs. Now for chapter 2, we're going to do exercise 8. Again, this is the question up here, and this is the G2 grammar it mentions in the question, just the 2 different ways it's set up. So the question is, the string, the girl touches the boy with the flower. So in G2 grammar, discussed in the textbook, there's 2 ways a sentence works. So a sentence can be broken down into basically a complex noun, complex verb, and a preposition phrase. Prep phase. A sentence could also be broken down with an article, a noun, and a verb phrase. So this is important for this one because the girl touches the boy with the flower. It has 2 different leftmost, starting from the left, deviations. So the first, using complex noun, complex verb, and prep phrase would be the girl is the complex noun. Complex noun. Touches the boy. Complex verb. And the prep phrase with the flower. So that's the first way to break down a sentence of the girl touches the boy with the flower. The second way would be the article, the girl, oh no, the article is the, technically here. The girl is the noun, so article, noun. And the verb phrase is touches the boy with the flower. And that is the verb phase. So, it's the same sentence, the girl touches the boy with the flower. However, it has 2 different leftmost deviations from just the G2 grammar of how a sentence can break down. You might be thinking, Joe, what do you mean? It looks like the same sentence, you just broke it down a little different. I don't think it means any different. However, it does. So here, with the complex noun, complex verb, and prep phase, the girl touches the boy with the flower. That means they're standing next to each other, and she physically pokes him with the flower. The flower is touching the boy. The girl is touching the boy with the flower. This bottom sentence is there's a girl and boy standing next to each other. The boy is holding the flower. The girl just reaches out and touches the boy on the shoulder. That is, the girl touches the boy with the flower. See how there's 2 different meanings for the girl touches the boy with the flower, or the girl touches the boy with the flower. Alright, so chapter 3 exercises. So this is the state diagram. So basically, we want to give the sequence that M2, which is this, enters when strings, when started on an indicated string. So basically, I'll try and go through all of these. So basically for 0, you start in Q1, because that's the start state, with a 0 next to it. And then you move Q1 to the right, and add a blank to the left. Then you're in Q2, and you have, and because there's a infinity, the tape's infinity, you can add a blank to the right as well. And then here, if you read a blank to your right, you move to the right and enter accept state. So for 0, 0, you start out at Q1, you move here, so you move to the right one, which moves the blank. So you get rid of the first 0 because it becomes Q2. Then you're here. So if there's a 0 to your right, you you add an X and move 1 to your right. So here you go, and we add the blank just because you can't run out of space. You're in Q3. Here, if there's a blank, you move to the left and go to Q5. So here's that again. So you got blank, Q5, X blank. You're in Q5 in here. So if you read an X to your right, go to the left, which we have. So it's Q5 blank, X blank. And then, so once you're in Q5, and you just move to the left, now you need a blank to your right to get out. That was supposed to be this one. Sorry. So here you move to your right because there's a blank to your right, and you shift into Q2. So now you got blank, Q2, X, Q2. Here, because you got another X, you move to the right of it and go right. Or you move it to your left and you go right. Wait. Oh, no. I misread that. I'm sorry. So you stay in Q2, but you move to the right of the X. So basically, you swap this to the right of the X, as you can see here. And then after this state, you're in Q2, and there's a blank to your right. So that means you move to the right and accept. Okay, so now triple zeros. Also, this makes sense because it's good to know going into it that this machine only accepts on powers of 2. So it would be 1, 2, 4, 8, and so and so. So 3 should not accept going into it. And we see that it doesn't, basically. Same thing with 6. So you start with that, move to the right, the blank gets added, get rid of the 0. Then from here, you again move to the right and add X. You're in Q4, and then you go from here, you have a 0, so you put an X and then move right. Here again. And next you have a blank, and if you look, Q4 has no movements for a blank. So you're trapped on Q4. Or no, it has one movement to go to the reject state, which you go if there's you blank to your right, and there is a blank, so you end up in the reject state. In the same way here, you gotta end up with a blank to your right. So I'll be honest, this was one of the most difficult things I did in the textbook, was these 2 exercises. And just really the way I learned to do them was just to keep practicing. I'm still not as good as I hope to be with them, but really the only way to get them is to practice. And it took a lot to learn, like what it meant when you move and how to move the actual like characters and everything on the tape. This was probably the hardest part of my learning, was figuring out like turning machines and how they move. So I'll just go quickly through this exercise too, because it definitely was the hardest to do conceptually for me. And it also was easily my most painful mistakes. Like I would forget to add blanks into these exercises, or I would move it the wrong way. So I'll say here, I would do like Q7, X, Q7. Going into this one, I would put another X here, say. It was just very hard for me to understand conceptually to read this, to read the state diagrams, and it just gave me a lot of problems actually figuring out how to write them. But the only thing I can recommend for you to do so you don't learn the same like mistakes as me would just be to make sure the thing I noticed with this textbook that if a good starting point is to try and do the first exercise, the first 2 exercises of every chapter. And if you can't do it, then go reread the chapter again. And then if you're still stuck, to Google it. Because I found out that the first couple exercises are good, just like depth questions of the actual exercise of the chapters. And if you don't know them, you don't know the chapters well enough to do any of the exercises. So it means you just have to restart and learn over. So this one is the same thing we saw in 3.1. So I'll just give you a quick run through. You start at Q1 with 2 1s to your right. You see a 1, so you plant an X to your left and move to the right. So then you have this. You're in Q3. From Q3 you have a 1 to your right, so then you move it to your right. And then you add a blank because the tape's infinity. And from Q3 there's nowhere to go if you have a blank to your right, so it just rejects. So with this one there is no outright reject state. However, if you get stuck, it's a reject. That's different than this where it has a reject state as well. That also was just turning machines in general were hard for me, and the only way like I was able to solve them was just practice and to keep doing them over and over and over again. Okay, chapter 3, exercise 5 now. So, here's the question, the statement, and the 4 preceding questions, notes. So, exercise 5 says, examine the formal definition for a Turing machine to answer the following questions. So we need, let's just say, Turing machine A. Okay. It's a 7-tuple, so it has that. Okay, so a Turing machine has 7 different elements. The first is Q, which is a finite set of states. Then followed by sigma, the tape. So it has an input alphabet and a tape alphabet. And these are not the same. They can be the same elements between both, however they are not the same. Q0 start state, so that's the state it starts at. QA is the accepting state. QR is the rejecting state. And what is it? Delta is the transition function. Those are the 7. That's the formal definition of a Turing machine. So now time to answer the question. A. Can a Turing machine ever write blank symbol on the tape? Can The answer to this question is no, it cannot. And that's because the tape alphabet consists of the blank symbol. However, the input alphabet, there is no blank symbol. It needs an input. It can't have blank as an input. That just wouldn't work. It needs to be like one string. So, no, the blank symbol is not in the tape alphabet. Sorry for the messy handwriting. Okay, B. Can the tape alphabet be the same as the input alphabet? I'm just going to do symbols. No, it's tape versus The answer to this question is no, they cannot be the same. Because the tape, just as we did in A, the tape consists of the blank symbol. However, the blank symbol is not found in the input alphabet. So that means the two alphabets are not the same. They can have similar things between them, however, they cannot be the exact same. C. Can a turning machine head be in the same location in in consecutive steps? Sorry about that. Can a TM head location consecutive steps? The answer to this is actually yes. I know you're probably thinking, how? It's because, so the tape is like this. And it starts at the farmost leftist position, the head. Say it reads the first thing in the state diagram and says, if you read a 1, move to the left. It will not fall off the tape. So it will just keep the head will stay in the same spot and just move to the next state and read the next command. So that's the only way the state will stay in the same spot. It will not fall off the tape going left. Last one. Can a turning machine contain a single state? Can a turning machine contain a single state? Alright, so I want you to look at this formal definition and guess if it can contain a single state. And yes, you are correct. It cannot contain a single state. We know it cannot contain, so no. We know this because it has to have an accepting and rejecting state in every definition of a Turing machine has this. And that's 2 states right there. So just the simplest Turing machines have more than 1 state. Alright, now we're on to chapter 4. And for chapter 4, we're doing exercise 1. Yep, chapter 4, exercise 1. Okay. So here is the image, and here are the 6 questions. No notes. Okay, so the image we provided is, the state image is 0. That's arrow. And the state has an arrow going to another state. There's an arrow going like this. Like this. 1, 0, 1, 2, 3. Okay. So that's the right picture. Okay. Now the first question is a Turing machine with the input 0100 a subset of, or an element of a DFA? So basically, is this Turing machine with this input a DFA? It's basically what this question is asking. The answer to that is yes. So the input is 0100. So starting off here at the start state, we go 0, stay there, 1, go to this state, then we got 0, we go to this state, and another 0, we end at the accepting state. So yes, because 0100 accepts, or ends in the accepting state. So the second question is M011 in a DFA? So is a Turing machine with the input of 011 a DFA? And the answer to this is actually No. We know this because 0, 1, 1 doesn't end in the accepted state. So 0, 1, 1, start here, stay, 0. 1 you go here, 1 you go here. It's not, you can clearly see it's not the accepting state. Question. So, let's see. Is M DFA? The answer to this one, so is M, a Turing machine of M, a DFA? The answer to this one is no, because that's not the right way to define a Turing machine. You gotta put M and then whatever the input of the machine is. So like M010 is an acceptable definition. Just the M is not acceptable. So no, it's not a DFA. D. Is M0100 so is M01, so is a Turing machine with the input of 0100 a regular expression, is what this question is asking? And again, no. A Turing machine is not a regular expression. If you wanted to write a regular expression, you would have to do parentheses R, comma, say the string, so like say A. That would be a regular expression, because it's, you define it and you say the input string. M, this is not how you define a regular expression, so no, it's not a regular expression. E is M a subset of a E DFA? The answer to this one is no. This question, just like this one. Because again, you can't define a Turing machine as just M. You need the other thing attached. Because we know, we've seen eDFAs, we've seen DFAs that worked, like this one in the past, and they have strings attached. There is no string attached to this definition. So no, it does not work. Final question. Is M a subset of EQDFAs? So is are Turing machine M and Turing machine M equivalent DFAs? And the answer to this one is yes. Yes, they are. They M and M2. So say this one's M1 and this one's M2. They both share the same language, the same Turing machine language. So they are equivalent DFAs. That's like asking if, that's like saying, is this equivalent with itself? And yes, it always is. The Turing machine is always equivalent with itself. So yes, they are equivalent DFAs. Alright, chapter 5. So basically this says, show that EQ-CFG is undecidable. And so overall you had to prove it. And the thing I've probably struggled most with, and the thing I wish I improved more in this class and just coming into this year, because I took discrete 1 and 2 and also problem stats, is my proofs. I always never write enough for proofs, and I always don't do proofs in the right format. Like, I just stray and I just kind of write whatever on my mind. So that's definitely something I could have done better in this class. But yeah, so here, so in the textbook it says that all CFG is undecidable, and we know all CFG is undecidable, and if all CFG, we know all CFG equals QCFG, so then we know EQCFG is undecidable. I know there's more steps to prove for this proof, but I'm just not 100% sure how to do it. Whenever I get these on exams, I just try to write as much as possible to prove it, and that's my proof. So that's definitely one thing I could have done better, and learned better from the textbook was how to write a proof. Alright, chapter 5, the last chapter. So I believe this, I didn't write this, I believe this is exercise 4. This is the PCP problem, the post correspondent problem. So it's basically just the 4 pieces you got to work with. So basically, it says, so PCP, you get pieces, you have to find a match. So say, just briefly to explain it, A, B, A, B, A, B, and then A, B, A, A. So you get these 3 pieces. And luckily for us, if you do the top and the bottom, and they cancel out, it's a match. So this with the top is A, B, B, A, and this is A, B, B, A, A. So that would be a match. Say a match wouldn't, say it's a lot harder when you have to do, say, A, B, A, and then B, A. When you have to do multiple pieces, so you might have to do this piece twice per se, all that. So basically that's PCP, and that's finding a match. So this example is you got these 4. A, B, A, B, A, B, B, A, A, B, A, 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 A. So you have these 4 pieces that you can use to try and find a match. You want the top to be the exact same as the bottom. Now this is very hard, and it's technically undecidable, but sometimes you can find a match. This is like, I really like this problem. To be honest, this is one of my favorite problems we've done recently, or exercises, because, so I've taken discrete 1 and 2 and prob and stats, and this reminds me just like it. It's how can you find this answer when you don't have anything given? So the key that I look for to solve these, now to be honest, there is a formula for these, and I wish I knew the formula better, but I just don't. I'll let the B here. So the way I solve it, in the a way to solve it basically, is so you want to find your starting piece. So we can cross out this one and this one for our starting piece, because right away they aren't the same on the top and the bottom. So we can start with piece 4 and piece 1. So we start with piece 1, it's A, B, A, B, A, B. We start with piece 4, it's A, A, A. So from here, these 2 cancel out, so we're left with A, B on the bottom. So what matches up with A, B on the bottom? We have this one, this piece, and this piece. So that's where we can go from here. So we can go, poop, poop. So we say A, B, A over A, B, and then B. So right away we find out this piece doesn't work. So then we do A, B over A, B, A, B, A, B. So then we're left with A, B. So these 2 cancel. We're left with A, B, A, B. So this, if we're being honest, looks like we're getting stuck in the same loop. So let's see what we got with this one. AA over A. So these 2 cancel, so we're just left with the A on top. So what can we go from there? We need an A on the bottom, and then everything the same. A on the bottom, but everything isn't the same. So right away, once these 2 A's cancel, we know we would have AB over BAB. Wouldn't work. A on the bottom, and it would just leave us with a B on the top. So technically that would work. Then we can also always go back to that. So let's break this up. So then we have A, B over A, adding this tile. And then this way we have A over A. So we're left with 2 A's on the top, or this one we're left with just B on the top. So from here we need B on the bottom, and then we needed to match up. So B on the bottom, all we have to do is this tile. So we would add ABA with B. These 2 would cancel out. And that gives us ABA. Here we need something to cancel out the 2 A's on the bottom. So the only one that would work for this would be tile 2 and tile 4. So we can break this up even more and do tile 2 on the top. So that would be AAB over A after the addition. And tile 4 on the bottom would be AAAA, so it would be trip A's alone after addition. So from here, we have ABA on top, nothing on the bottom. AAB with A. We have AB on the top with nothing on the bottom. Or we have AAA on the top with nothing on the bottom. Those are the 3 possibilities we have. So we need ABA. So what we could do on this top one is do this piece, because that would match up. So we add AB with, or just AB with a AB, and that cancels out these 3. However, we notice it leaves A and a B. No, doesn't work. So that doesn't work. We go down to this one with AB. And what could we add? So the first 2 on the bottom have to be A and B. We could add this. No, no, no. So this pathway, we're just stuck with adding A over AB. So we add A over AB. And luckily, cancels. So that pathway works. So this is my strategy going about it. And I've kind of been always a fan of just the most complex way to solve things. Like I always kind of brute force it, because I just, as a computer scientist, it's kind of like a hacking thing. Like I always think it's cool how you can brute force stuff, but in actuality there is a equation for this, but we just found it. So what we did to get there was technically we did AA over A, AA over A, then we did B over A, and AB over AB, AB. So the top, that equals AAAA, BAB. The bottom, that's AAA, ABAB. And you notice that's the same on the top and the bottom, so it's a match. Now, I'll be honest with you, this was one of my favorite exercises to do just from a mental standpoint. I loved the kind of challenge you had to do of solving it, and it was one of the funnest exercise I did. However, I would love, there is a formula that I know how to do. I know what it is. I'm still lost in how to do it. So that is definitely, if you take this class, one thing I would definitely suggest learning, because these are the funnest exercises, I would say. And yeah, so that is all the exercises from chapters 0 through 5 and everything we've learned, basically what we learned so far in the class. I hope these exercises have kept you interested and you want to learn more, because I would definitely recommend taking this course. It's a lot of fun. See you, man.